Hi everyone. Today we're going to start our unit on complex analysis, which will help us eventually develop some tools to solve some tricky integrals that you might encounter during your first and second year coursework. It turns out very often integrals are easier to solve if instead of evaluating them as they're written, we transform them into being functions of complex variables, and we use some tricks that we'll develop in a few videos down the line. But in order to develop these tools, we need to build up a theory of complex numbers, understand how complex numbers fit on the complex plane, and so that's what we're going to do right now. So, probably familiar that we can write complex numbers like this, x plus iy, where x and y are some real number that we can plug in. And this complex number is separable into real and imaginary components. Our real component of z, we could write like this. Our real component of z is just x. And we could also refer to our imaginary component of z by writing it out like this. And the imaginary component is just y. Careful not to write iy. Our imaginary component will be a real number that we multiply times the imaginary unit I to get our full imaginary portion. So, we have this complex number, and we can graph it on our complex plane. We could not put this on a Cartesian plane with x and y axes, but instead we have to graph it on our complex plane, which has a real axis and an imaginary axis. So, assuming that both x and y are positive numbers, we might have our complex number z be somewhere like right there. And so, z would have an x component on the real axis and a y component in the imaginary axis. So, the complex plane is quite different from a normal Cartesian plane, right? If we had y and x axes, normally x is our dependent variable, y is our independent variable, and we can plot out functions normally on the axes. It would be hard to plot a function on this axis. Most functions will not end up being plottable on these axes. So instead, this really just maps out sets of complex numbers. We might be drawing paths through this space that complex numbers take. And so this xy parameterization often isn't the best way to write our complex numbers. So just like we can parameterize space with Cartesian coordinates or polar coordinates or cylindrical coordinates, we can also parameterize our complex number space in different ways. We'll see that it's sometimes better to write these complex numbers in a polar form, and I'll do that right now. So, to get there, we would need to rewrite x in its polar form, r times cosine theta. We would need to rewrite y in its polar form, so plus I. Y will be written as r times sine theta. We can factor out the r. Cosine theta plus I sine theta. And in case you don't recognize this term in parentheses right here, this is equal to e to the I theta. This is an identity that pops up all the time during first year. It's called Euler's identity. And it's a very useful way to transform between our trig functions, cosine and sine, and complex exponentials. So, now that we've written our complex number in this way, let's see how that shows up on our complex plane. We would have r, which is the distance from the origin to where our complex number is, and theta is equal to the angle of rotation between our complex number's position vector and the real axis. So, It turns out that this is a lot more useful to us in a lot of cases. And really the first way we might see this is if we try to multiply together two complex numbers. If we wanted to write out two complex numbers, we'd have to choose, do we write them x plus iy, or do we write them in this form? So if we had two complex numbers in this form, and we multiply them together, we have to FOIL out all the terms, x times x, iy times iy, x times iy, and so on. And we have to keep track of the i's. Sometimes we'll have I squareds that turn into -1. It can be a little annoying, but we'll see that if we multiply them in this form, we get a little bit of a geometrical understanding of what's happening. And it's very useful to understand complex conjugation through writing things in this way. So let's go ahead and just generally write out the product of two complex numbers. I'll write out z1 in red, which is r1 e to the I theta 1. z2, I'll write in blue, r2 e to the I theta 2. And if I take the product of these, z1 times z2, the r's will simply multiply together, r1, r2. And when we multiply these exponentials together, we can add what's in the exponent and combine it into one new exponential, which would look like theta 1 plus theta 2. So if we think about what's happening here, theta 1 plus theta 2 means we're combining the angles of these two complex numbers. So if we multiply times a complex number, it's like we're rotating our original complex number by some new angle, especially if our values of r are 1. So we'll go ahead and see how this works by taking a complex conjugate and evaluating the norm using this form. So our complex conjugate is where we take our complex number and we flip the sign of our imaginary component. And we could either write that, there are a few conventions. One is z bar for the complex conjugate, another is z star. And we could write this as x minus iy. That's one way that we could complex conjugate this. But if we wrote our other form, we could equivalently say that this is equal to r e to the minus I theta. And so what this does, if we plot where this is on our complex plane, it's a reflection about the real axis. We have the same real component, and we're flipping our imaginary component, and so we would end up having z star be somewhere down here, where we're the same distance away from the origin, the same x component in the real axis, but now we have a negative y component, or in other words, we have a negative theta rotation. And so when we evaluate the norm, which is the absolute value of z squared, which is z times z star. Again, less useful to try to FOIL all of this out, and more useful to use this form. We can see we will have r. If we just plug in this formula, both of them have the same value of r, so that'd be r times r. The exponential, we have theta 1 plus theta 2, which the thetas here are theta and minus theta. So this is theta minus theta. We end up just getting 0 as our exponent. And if our exponent is 0, the whole exponential turns into 1. And so we're just left with r squared. So what's happened when we've multiplied these two complex numbers together is one of them is rotated by some angle theta. By multiplying times the second one, we've rotated back an angle of minus theta, and so our result is something that is just a real number, something that is on our real axis. All right. So this is something that shows up a lot, these rotations of complex numbers. And to get an idea of why they show up so frequently, if we think of our position in complex space as a complex number, again, r e to the I theta, and we want to understand how it changes with by modifying theta, or in other words, if we take the derivative of our complex number with respect to theta, we would get, if we take the derivative of this, it's just the derivative of our exponential, the derivative of an exponential, we end up getting I pops out from here, r e to the I theta, which, if we look at this part, this is just our original complex number. So this is I times z. So if our original complex number was just on the real axis, pointing this way, our derivative would be pointing with a real number times the unit, imaginary unit I. So our derivative would be pointing straight upwards, straight in the direction of the imaginary axis. And so this in general is true. If we take the derivative of our complex number, we get a result that is multiplying times I. And multiplying times I is equal to rotating our complex number by 90 degrees.